In the name of God, in this tutorial video, I want to demonstrate how to use the LabVIEW software as a Modbus master to control a Modbus slave device. So we need also a Modbus slave device. It can be either physical or virtual. For the simplicity, I decided to use a virtual Modbus slave device. A virtual Modbus slave device is implemented using a simulation program like Proteus, which is a system modeling suite. Its description is outside the scope of this tutorial video, so I just open it and get familiar with it quickly. Maybe in another tutorial video I explain how to build such a virtual Modbus slave device. I already created the simulation and saved as the AVR board file. As can be seen, at the heart of this design there is a AVR microcontroller, actually an AT-MEGA32. The communication between this microcontroller and the Modbus master is created by a component which is named in the Proteus software as CompIM. The microcontroller already loaded with a software named Modbus AVR that acts the AVR microcontroller as a slave device. The CompIM connects to the physical port of the system COM3 with a baud rate of 38400, a database without parity. There is 4 input-output connected to the microcontroller. Actually, the light emitting diode green D1 acts as an input, and the microcontroller turns it off and on each 1 second. The D2 is actually a coil, and the Modbus master will turn it off and on. Also, there is 2 analog input. One is connected to a potentiometer and the other to an LM35 temperature sensor. The signal is amplified by an amplifier, which can be seen here, and use an op-amp to amplify it by a gain of 5. And this is all our Modbus slave simulation that we use as a Modbus slave device virtually. Well, let's look at the requirement for the LabVIEW to be the Modbus master. The software components include the core component of LabVIEW. Here is LabVIEW 2012. NI Visa 5.2 is already installed. NI Visa is needed. Also, the data logging and supervisory control module should be installed on the system. So there is 3 requirements: the core component of LabVIEW 2012, NI Visa for the serial communication, and data logging and supervisory module to understand the Modbus protocol. Also, there is 2 serial ports physically connected to the device, COM1 and COM2. We cannot use these 2 ports which are physically connected to this computer. We use 2 virtual serial ports. For creation of virtual serial ports, we use virtual serial port emulator program, which is freely available. There is many options. I use a pair that defines 2 serial ports for the system and connect them virtually. The 2 serial ports are named COM3 and COM4. COM3 is already connected to the Modbus slave through Proteus simulation software, and we use the comma 4 for the LabVIEW software. Well, it is now defined and initialized. So we minimize the window, it is running, and we now run the simulation program, and the Modbus slave device is ready for our demonstration. After the simulation starts, we focus only on the inputs. As I described, the D1 is periodically turned off and on each 1 second, but consider that the simulation is not real time, so the time may differ actually from a physical device. The potentiometer can be increased and decreased, and the temperature can be increased and decreased accordingly. The T2 is also controlled by the Modbus master that we wanted to implement in the LabVIEW environment. Okay, this is our Modbus slave part. Before running the National Instrument LabVIEW 2012, we should add the comma 4 to the definitions of the COM ports defines for the National Instrument variable engine. So we use the control panel to restart the NI variable engine service. At the control panel, use the performance and maintenance shortcut to reach the administrative tools. In the administrative tools, double click on the services and scroll to find the NI variable engine service. This is the one we want. It is already started, but as the system boots, only 2 ports are available. We added 2 other, comma 3 and comma 4, and we should restart the service to find these new ports again. The restart of service may include an error message, but don't panic. Continue and click OK. OK, don't send. It will work fine. OK. Now the comma 3 and comma 4 is defined for the National Instrument system. Okay, we run the National Instrument LabVIEW 2012. As the splash screen appears, you can see the LabVIEW 2000 registration codes, and also there is a icon, there should be an icon on this splash screen that you can see here. There is 2 computers with an op-amp sign on them. It signals that the LabVIEW 2012 is equipped with the DSC data logging and supervisory control module, which is required for the LabVIEW to become as a master, Modbus master. The next step is creating a new project. So I choose the create project. The next screen is wizard that guides me through different types of project available in the LabVIEW 2012, but I use just a plain blank project. Plain blank project is sufficient for our purpose. I choose the blank project and click on the finish. The first step should be to save this project. I save it on the desktop in a new folder. Named AVR system, and also I assign the name AVR system to the project name. Okay. After creating the project, the empty project, I right click on the My Computer icon in the project and choose an I/O server, new I/O server. In the new pop-up screen, there is plenty of different I/O servers. At this moment, we choose the Modbus to identify the LabVIEW as the Modbus master. If you want to LabVIEW act as Modbus slave, you should choose the Modbus slave. But at this moment, we want the LabVIEW to be a Modbus master. So we click on the Modbus and then click on the Continue. The next screen configures the Modbus communication parameters, such as COM4 as the communication port used between LabVIEW and the virtual Modbus slave device simulated by the Protos simulation software. So we choose serial port COM4, baud rate 38400, without parity a database stop bits. The other parameters is specific to the Modbus protocol, such as the Modbus slave address. In the microcontroller, we define the address as 10, so we change the address from 1 to 10. The other parameters are not considered at this tutorial, such as alarm parity, refresh rate are 8 and 1 second, they are fine. We increase the time delay, which is already half a second, to 5 seconds, since the Modbus slave is virtual and it runs slowly than a physical device. Retry attempts 4 is sufficient. Transmission mode is RTU by the microcontroller. Since the time out delay is increased to 5 seconds, we increase the wait if fail to 15 seconds. In this tutorial, the Modbus protocol is over the serial port, but the LabVIEW can work with the Modbus slave devices through Ethernet. So the Modbus serial selection is fine. Now I can click on the OK, and the I/O server is added. I renamed the I/O server as the I rename it as the or I can right click or two-line click and rename it to 80 mega 32. It is optional. Now I can save the I/O server defined to save the parameters. Again, I choose to save. Okay. The project is already saved, but the library for the I/O server is also saved at this step. Okay. Now we define everything for the communication with the MOSFET, but the input and outputs are not already defined. For the definition of the input output, we right click on the Modbus slave device, which we named here as ATmega32, and then we should choose create bound variables. For creation of bound variables, there is a specific rules which should be memorized. But if you want to not memorize these settings, you can choose the view IO items. This is a guide. Well, when clicking on an IO item in the left pane, we see an item description in the right lower pane. We have two single bit coil for two LEDs, and we should choose the address range between 1 and 65,535. Also, we have two input registers, and we can see that the addresses between 300,001 to 365,535 as the 16-bit input registers. So we use these two ranges for defining coils and input registers. Okay, so click on the create bound variables, expand the plus close to the AVR system and AVR system IO server ATmega32. Now we go to the single bit coil address range and click on the add range. The address of these two coils, which is connected to the two LEDs, is at the address 2000s. So I enter the data item as 2000s and the number of items as 2 and click on the OK. When I click on the OK, the other settings which is regarded for reporting and alarming is also can be changed, but we don't talk about these parameters at this presentation. So we click on the OK. Also, we can rename these two coils at this moment. Rename green LED and red LED. These two LEDs are defined in this system. The other variables are the analog input 16-bit integer values, which should be added from the range of address 300,000. The registers are located at the address 3,000, and there is two 16-bit input registers. Again, we do not configure other options and just click on the OK. Also, we rename them as potentiometer and LM35. Okay, so we define all the four inputs to the Modbus slave system. We save the project and libraries. Now we should deploy the IO server. Every IO server should be deployed before usage. So I choose the AVR IO system server and right click on it and choose the deploy or deploy all. Deploy all is better. All the Modbus communication protocol settings are now deployed and will be in operation. When the deployment finished, writes this message: deployment completed successfully. Okay. Now we want to see the variables and change the outputs like T2. We choose the tools menu in the project and then choose the distributed system manager. In the distributed system manager you can watch the variables and also change the outputs without writing any code. It takes a while to see the distributed system manager screen. Okay. As it can be seen, the green LED is periodically turned on and off, and you can see it is true or false. When the LED is on, it is true. When it is off, it is false. Since the logic is used is active low, so it complements. This is true again for the red. We see that it is true, but in the simulation program it is off, since the logic is active low. If I set it false, you can see it now turned on. Also, the readout of the LM35 can be seen. It is reported as millivolt and amplified by a gain of 5. I decrease the temperature to 20 degrees centigrade. LM35 produces 200 millivolt and it is amplified by 5, so I should read 1000 millivolt. It is approximately 1000 millivolt. If I increase the temperature to 30 degrees centigrade, so the voltage will be 300 millivolt and amplified by 5, so I should read 1500. Let's do it. The temperature is 30 and the readout is 1513. Also, the potentiometer can be adjusted. Now it is in the middle, so it is half the VCC. VCC is 5 volt, so it is 2.5 volt or 2500 millivolt. If I scroll to the top, it is increased to nearly 5 volt, which is approximately 4995. And if I scroll it to the bottom, it will be close to the 0. Actually 4 millivolt. Okay. We use the display system manager to check the parameters of the Modbus slave device without writing any code. Let's proceed to the next step, writing a code, simple code. That can demonstrate the status of the D1 LED. At this moment, we can deploy to break the communication with this LabVIEW as the Modbus master with the Modbus slave device running in the Proteus simulation program. At the My Computer selection, I choose a new VI. A new VI program, virtual instrument program, is open. I want to periodically read the status of the D1 LED and show it on the front panel. So I use a structure, a while loop structure. that runs periodically. On the front plan, I add a button to stop this loop. Okay. At the block diagram, I connect the stop button output to the condition of the while loop. Well, I want to report the status of the green LED. So I add a LED, a round LED, out to the front panel. The status of the green LED is indicated in this Boolean output, but consider that it is active low, so we must complement the output. I just drag and drop it to the block diagram. Just this simple one. It is very simple to read the Modbus parameters and or write them. And in the programming, I choose the Boolean and the not function to put between them, and then wire So reading the Modbus slave is very fast is not a good idea. I choose a timing such as wait, and I create a constant for 100 milliseconds. Actually, I force the green LED be read from the Modbus slave 10 times a second. Okay, now we can run the VI. Before that, we can save the VI. I choose the name AVR HMI, Human Machine Interface, and now I run the program. Automatically the program deploys the Modbus devices, and after successful deployment, we can see that the front panel is working accordingly, but with a small delay, which is normal in the simulation program. Okay, we conclude this tutorial: how to connect with a Modbus slave device, how to produce an HMI using LabVIEW development software. Thank you and good luck.